All right, so I'm presenting today, but Adam Atchley on our team at Los Alamos, the Earth and Environmental Sciences EES 16, did most of this work with some help from Kelly Crowell, who's now at Neptune. Kelly started at Los Alamos many years ago as a student and then moved on to a contractor position and ended up working for Neptune. So I'm going to be talking about Area G, which a lot of you saw yesterday. It's out on the mesa to the east, towards the east end of the laboratory. We've got an image there. Oh, good. Now I'm moving. We got a picture of MDAG down there on the bottom. It's a 63-acre site, operated from the late 1950s up until the present day. The northwest pit is still receiving waste. And what I'm going to be talking about today, we've heard the 435 performance goals of 1,000 years, but last year our DOE regulator at Los Alamos, Hai Shen, asked us to look at 10,000 years. And so we started scratching our heads and saying, well, we haven't done that before, but we'll give it a whirl. And so today I'm going to be presenting our initial results on a 10,000-year erosion calculation. And so we have a suggested cover design that's meant to keep the waste in place, keep those inadvertent intruders from getting a significant dose if they come in and put a house on the site or drill a well through it. And I've got a conceptual model on this figure showing the very dry mesa top. We think that with a vegetated cover, long-term infiltration fluxes are going to be on the order of 1 liter per meter squared year. That's a millimeter a year infiltration. I don't like to say a millimeter a year because everyone thinks that's how fast it's going, but that's actually a flux. If you had a crack that was, 1 millimeter, then it would go a meter a year. So to do this erosion modeling, we use a program called Siberia. And a lot of people ask, well, why is this erosion model called Siberia? If you look at the red square, those two terms are slope and area. And when this was first being developed, the guy that developed this would say, slope area. And people thought he was saying Siberia. And the name just stuck. So this is the strangest name of a simulator that I've ever heard of. So it predicts sediment transport derived from shallow sheet flow. This is not a discrete event simulator. We're not simulating large mass transfer due to discrete events. This is a simulation of a gradual erosive process, a yearly average or a 10-year average. And the spatial distribution of deformation across the complex, we predict. We have a three-dimensional cover that was developed based on some modeling done with Siberia. So we have a 63-acre site. We know how deep it is to the waste. We knew it had to last for 1,000 years, so iterating on different peaks of that cover and thicknesses at different points around the mesa top, we were able to design a cover that would erode preferentially in certain areas and protect the waste from getting less than several meters of fill on top of it. And that is protective of the plants and animals and the intruders. At this site, we really don't have much of a groundwater risk. It's been pointed out, 1,000 feet to the water table. So the governing equation, I'm not going to go into that, but it really does depend on the slope in the area. The sediment flux going through a single grid cell is based on the slope in the area, and the second term, also important, has a diffusion coefficient, and that's how fast the sediment will diffuse. And in a diffusive system, any peaks will get softened out rapidly. A non-diffusive system, the peaks will stay in place and you'll get valleys cutting down in between them. So some of the limitations of the Siberia model, this, I hate this, geomorphically effective event assumption. That just means we're averaging over the year. So we're not doing discrete massive runoff events like that 13-inch rainfall. So the model has been calibrated and validated as much as we can. We don't have 10,000 years of measured data. What we have are long-term events, long-term erosion at the Walnut Gulch experimental watershed from 1964 through 2007. We also have experimental waste covers at Los Alamos that we've used to try to get at some of these parameters. And another line of reasoning that we use is we set up the model with the best parameters that we have. We run it, and we look at how the topography evolves through time, and we compare it to the known topography to see if we're wildly out of whack. But there's big uncertainties in this erosion modeling. I mean, I would be comfortable with it over 50 to 100 years probably, but 1,000, 10,000 years, especially with climate change, with other uncertainties, don't know what's going to happen in 10,000 years. But we have made some calculations. It's a complex workflow that's needed. So in number one, we're running simulations with the IRIS model and the HEM sediment flux model that are then used to generate parameters to feed into the Siberia surrogate model. And numbers 2 and 3 are where we feed in our digital elevation model and topography of the planned cap over the waste and the bedrock and the armor. So for this site, we could not just let a crushed tough cap on top of the mesa. We got too much erosion. So this model has built into it bedrock and armor around the entire 63-acre site. So you can imagine granite boulders. It's starting to sound expensive, but probably not as expensive as digging up 63 acres of waste. And so all these things then feed into the Siberia model runs, and we get erosion and gully formation. So parameterizing that Siberia model, this is, if we go back one slide, number 1 has those arrows that connect down to the number 2 and 3 calculation, and that's what this slide is representing. We have the colored figure on the lower left for you guys is a type simulation that we use to generate the parameters we need to feed into the Siberia model. A lot of text there, I'm not going to go through it all, but it's an iterative process where we have to run on different slopes with different erosion rates to figure out what parameter we need to feed into the Siberia model using a sediment transport model. And we have validation. This is some examples of data. This is all data on this figure from MDAG small watersheds, from TA51, another site at Los Alamos, some runoff plots that were built, and from the canyon just north of our waste site. And these are total suspended sediments in the catchments that we have measured. And so we've got model results that match within the bounds of the uncertainty in these estimates. And so this is a list of the parameters that go into this model. Soil texture, which, we have a ground cover, landscape forming return interval. We have runoff, and then those are used to tune the Siberia model parameters that I showed in the equations earlier, the slope and the area, slopey area, and the diffusion coefficient. So what we've done for this particular set of demonstration simulations is to generate a low, moderate, and high example. For the PA, what we would do is have a range of simulations, maybe 50 or 100 of these, that would span the uncertainty space. But for this demonstration today, I'm just presenting 3 cases of low, moderate, and high. And even with 3 cases, what we're going to see is that there are trade-offs. In the high diffusive system, you get impacts that are not necessarily intuitive. There's trade-offs. And, so this is showing the location of the bedrock and the armor. The red on the one figure up there is the bedrock and armor all around the site. I'll point out that We all saw yesterday, or anyone that was on the field trip saw, that there's cliffs surrounding Area G. All of the waste, by dictate, has to be at least 50 feet back from those cliff edges. So the riprap and the boulders are going to be back from the cliff edges. And the next talk we're going to hear today from Liz Miller at Los Alamos is going to be on cliff erosion, cliff retreat. And so that 50-foot buffer is pretty important if those cliffs are starting to drop away in the next 10,000 years. So this is an image of the Area G cap. The engineering covers paste over the pits, to reduce infiltration and transport. Reducing infiltration may increase runoff. It will increase runoff. We have these newly formed slopes. And will increase the erosive force for gullying. And so as I described before, this cover was designed to focus gullying in areas where we could afford to lose cover. Places where the waste is either deeper or where there isn't any waste. And the cover, the minimum thickness on this cover is 3 meters, so 10 feet. And there are places where the crown of the cover reaches in excess of 20 feet deep. So this cover is not going to be inexpensive to build either. But we have waste sitting on a mesa that's eroding. It's a fairly unique situation. I wish we were in Utah in a basin, a sedimentary basin with a clay cap rock on it, but we're not. This waste started going in the 1950s, so we didn't have much of a choice there in the present day. So these are results for the 1,000-year elevation change with the low erosive potential on the left, moderate in the middle, and high on the right. And you can see as the erosion potential increases, we start to get the blue and green, the blue and up to green colors are cutting down. The orange and red is material being deposited. So in all these cases, we're dumping material into the small canyon that's located right by the 33 shafts that Neptune's working on. There's retrievable transuranic waste right at that location. But these results are showing that the cap is doing what it's designed to do. That area where the maximum erosion is an area that we chose to give up. There's not waste directly under that, but we put a cap on it so that it could erode without impacting the site. That's at 1,000 years, though. So now we're going to go out 10 times longer. And you start to see that at 10,000 years, this is where the non-intuitive results come in. The moderate erosion is allowing higher slopes. It's not smoothing it out as much. And so the center of the trench where it's cutting up from that little valley actually gets deeper than the high erosion case, because the high erosion case is cutting more of the entire cap down, but not focusing the erosion into discrete channels. And so you can see that this slide is to show that the riprap is working. There's a very discrete change at the edge of the mesa where the riprap is. It's not eroding at all. And so we're cutting material from the top of the cap and dumping it into the canyon. One of the things that these 10,000-year runs pointed out was that in the absence of large discrete rainfall events, we are unable to sweep out the sediment that accumulates in that narrow canyon. And so we're building up a pile of sediment there that we don't think is realistic. And that's one of the limitations of the Siberia model. But we think the erosion cutting down onto the cap is realistic. So that's what we're really after. What's going to happen is these simulation results from the cap are going to be fed into our GoldSim model. Rick's in the audience here today. The GoldSim model marches through 1,000 years or 10,000 years, and at each time step we have the distance from the waist to the top of the cap. And then we have a rooting depth, and we have plants and animals that are trying to do what they do. We have an intruder that comes in and puts a basement in. And as that cap drops through time due to this erosion, depending where you're sitting on the surface of the 63 acres, there's a probability that that basement now is being dug into a waste pit. And that's when the doses really go up. And so for the 1,000-year case, our intruder doses get very close to the 100 millirem a year maximum. For the 10,000-year case, we haven't run that yet. We've just generated our erosion files, and now we have to implement those into our PACA. We're hoping to do that this year. Our funding's a little bit uncertain. And so this is showing the deltas. Another figure showing the erosion at low erosion and high erosion, but with the pits laying on the top. And you can see how the cover was designed so that the erosion, the maximum erosion in that blue finger on the top image that's cutting back in, is not actually on top of a pit. And so that's it, if you have any questions.
Yeah, we do have time for a couple quick questions for Philip's presentation. Then Liz, after the break, Liz is going to follow up to present the cliff retreat study. Yeah. George. Pass on that to...
Hi, thank you, Phil. George Alexander. Thank you for the presentation. So using Siberia, you've assumed that steady state erosion controls, or steady state conditions control the erosion. What information do you have that episodic events don't impact the erosion?
Well, I would like to say that they do impact the erosion, but we don't have the capability to include those yet. This is our best model that we have. Could you repeat the question? Oh, the question is, what evidence do you have that discrete events do not impact the erosion? And my answer is that they will impact the erosion, but the model we're using doesn't capture them yet. And we would like to get to that point, but if you look through the models that are available right now, we just don't have that capability.
Thank you for bringing this up, George. Actually, in the audience, sitting in the audience, we have a couple people working on a similar issue at the West Valley site. I hate to put you guys on the spot, but Paul or Zintas, you have to address similar questions that have been raised. Yeah, or John. Erosion. Episodic events on effects on erosion studies. What type of model might be suitable for modeling that kind of process instead of
type of model? So I have a comment rather than address the type of model. I think I'll address it differently. So Pole Black Neptune. And while I understand in principle that's what happens, it's episodic events that drive this, like Phil says. But we're modeling a system, and we're modeling long time steps in that system. So assuming we're modeling those long time steps properly, with rate equations or whatever you have in Siberia, but there's some form of rate of erosion going on in there. If the rate of erosion is estimated properly across the episodic events, then we're capturing what's going on in the system. And that's what matters.
But aren't your rates of erosion based on steady state erosion rates?
I don't know where Phil got them from, but...
No, they're parameterized based on actual field sites.
Right.
So they do include, that field site in Arizona could have, 1964 through 2007, it might have had a 1,000-year event. It might not have, so.
So it was coincidental that we end up working on two projects that erosion's a driver, Los Alamos and West Valley. And it's the same thing at West Valley, where there is a group that's doing a very complicated erosion model where they're potentially trying to deal with episodic events, and we're still looking at it saying, yeah, but look at our time steps and look at the purpose of our model. It's to understand what's happening to the system. We don't care if there's an episode next week or 3 months from now or a year from now. If our time step is 10 years, why does that matter?
I do
All that
agree with
matters
you,
is
Paul.
what happened over a long period of time. Oh, heck yeah. But so long as you have the data to support that, where data is either data or some form of information, wherever that came from, that's what you need.
I do agree with that, but we do end up with some non-physical canyon filling, we think, because that canyon hasn't filled in. It's kept that shape with the steep canyon and a relatively flat bottom. But I guess we weren't dumping this much sediment into it. So maybe that's what it would look like.
Well, and maybe that means that there's some data or information collection or other modelings needed to support it. Maybe you need to wash the sediment out, like you said, which would happen naturally.
Yeah. To get back to George's original question, though, I believe, George, maybe your group is also reviewing the West Valley work down the road, so that's where he's coming from. So my hope is, Philip, you can get in touch with the West Valley subgroup that Zintas, can link you with, and you guys can compare notes on the type of model that could be suitable, as a benchmarking tool set or whatever you want to do to compare to the Superior model work that you have been doing, at least to give you some insights as to whether you need to make improvement or not using Superior. So, thank you.
One more response on that.
Wait, you cannot speak because we want to capture your comment.
On the record.
Okay, one more comment on that. One thing that we found at West Valley, then, I don't know if you've looked at this at Los Alamos or not, but we have photographs going back to 1939 that are being digitized. And we think probably that 80-odd year record is probably better than trying to model a 14,000-year record when we don't know what happened for most of that time. We can sort of guess at it. But it's undoubtedly a non-linear erosion over that length of time. The 80-year record's probably better. You probably have photographs of Los Alamos going back to the
Yeah,
mid-40s
Liz is shaking
too.
her head yes, and we are also pursuing, nodding.
And that's probably better than trying to do some fancy process level modeling, but we'll see.
Great, thank you. Any other quick comment or question for Philip? He's ready to escape. Any other one? Yeah, John.
It seems like another closure approach that would avoid the whole problem of now having focused recharge or focused surface flow that's causing extra erosion might be to remove part of the top of the waste, and then if you could get to the point where you could close it at grade, then nature will be very happy, and erosion, surface erosion becomes a non-issue, and then you're just back to the cliff erosion.
That's a great idea, John.